Okay, this is Michael McClellan. Thank you so much for attending another webinar. And today we have a very special guest, Mike Vukovitz, who has worked extremely hard on this presentation. And this is a presentation that we've been discussing for quite a while. I feel like it's necessary for the electrical community because there are many arc flash relay options out there nowadays, and it's a little bit confusing to understand what relay does what and what method are we using to reduce the total clearing time. And so Mike is going to explain the different components that make up total arc clearing time, which certainly affects our arc incident energy. And so a couple of housekeeping items. We would love for you to ask questions. Please use the question box on the right side of the screen. There is an icon. It's, I believe, a magnifying glass. It may be a question mark, and you can press that button and enter questions, and we will try to respond to them at the end of the webinar. Thank you so much, Mike, again, for joining us. And now I'm going to turn it over to Mike.
Good afternoon. Again, my name is Mike Vukovitz, and it is, as always, a privilege for me to be with you here today. And I appreciate you taking your valuable time to listen to this presentation on comparative models for low voltage and medium voltage systems with respect to arc flash mitigation. If you came here today looking for a cutting edge, I think exciting presentation, some new developments in terms of information that can be provided that will be provided with respect to arc flash mitigation, you come to the right place today. If you came here today expecting a very well polished presentation that isn't in need of a lot of improvement, you come to the wrong place. So this is literally a hot off the press presentation to you today. Michael and I have been discussing this, and we could have waited longer and spent a lot more time and effort polishing this up and even gathering additional data. But we want to give you this presentation today just because we are so excited about the results and the information that's presented in it. As always, we encourage questions in the chat box, and we look forward to participating with you after the conclusion of the presentation as well, if you have any questions. The presentation today, 90% of the slides in this presentation are brand new, have been developed just over the course of the last week. This is not one of those slides. This is a slide obviously showing an arc flash event. And the presentation today, to be clear, in terms of the audience and the purpose today, is not to discuss arc flash and why arc flash is bad and how to model for arc flash, any of those issues. In addition, some of the specific topics such as arc flash quenching are mentioned and modeled in the presentation today, but are not gone into in detail. There are separate L3 presentations on those subjects if you're interested. So this is the only slide we have showing arc flash itself in the presentation. And for those of you who are unfamiliar with arc flash, again, we don't have time to go into detail. If you are interested in a separate arc flash presentation, please contact your L3 sales representative. What I can tell you about arc flash in terms of my personal background is that one of my best friends was killed in an arc flash event. And when I went to the funeral and met his widow and the 3 young children who were growing up without a father at that point. I was informed by another attendee at the same funeral that a technology existed to permanently eliminate these type of events. And this occurred in August of 2001, and it had a dramatic impact on the future direction of my career as well as my passion for arc flash safety. I've given depositions now or advice in 17 legal cases relating to arc flash events, and I do believe that arc flash mitigation and with arc flash relays and arc quenching and the technologies we're presenting to you today aren't just good ideas, aren't just nice to haves. It's something that ethically, as engineers, we should be incorporating into every electrical distribution system that has an arc flash incident energy over 1.2 calories per centimeter squared at the IEEE 1584 working distance. So briefly here, arc flash is 3 times as hot as the surface of the sun. It's deafening, over 2 million lux of light. If you look directly at it, it'll score the cornea of your eye. The explosive pressure is sufficient to knock you off a ladder, blow you back from the equipment, and cause physical damage to you. And the pressure itself is sufficient within the arc flash boundary once you get above 40 calories per centimeter squared to collapse your eardrums and your lungs. The average cost of an incident is $500,000, more than $500,000, but that's deceiving because so many are small arc flash incidents. It masks the fact that many of these incidents are millions and tens of millions of dollars of equipment damage and liability due to personal injury. And there are approximately 5 to 10 incidents per day in the United States. I want to make clear that the presentation today is actually not about this picture. Although personal injury, is absolutely one possible outcome of an arc flash event, the primary purpose of today's presentation was to illustrate models of clearing time, but also illustrate the amount of damage that takes place to the equipment itself, the critical equipment assets. And where the arc flash takes place inside the gear is at much shorter distances than the working distances that are identified by IEEE 1584, where a person would normally be working on the asset. And those working distances for low voltage assets are 18 inches. And for medium voltage assets are 36 inches. So as you'll see in the models that we've constructed for the physical assets that we're going to be discussing today, we modeled those at 1/3 of those working distances, and we'll show you the results of that modeling as well. This slide, which I put in every single one of my presentations, is the arc flash mitigation toolbox. And it prints very well on an 11 by 17 piece of paper. It's not the purpose of this presentation to go through everything on this sheet here, but I do offer it to you as a handout. So if you contact your L3 sales representative, they can send you an electronic copy of this. This version prints on 11 by 17. There's a separate version they can send you that prints very well on 2 separate sheets of 8.5 by 11 sheets of paper. And what this is every approved arc flash mitigation method under NEC Article 240.87 and NFPA 70E Annex O.2.3. So the summary of this sheet is it lists the arc flash mitigation method. It describes the mechanism of how that arc flash mitigation method reduces arc flash incident energy, the benefits of that method, the approximate clearing time, meaning how quickly does it clear the arc flash event, and any drawbacks associated with that method. And I want to be clear, both Tech 4 and L3 support every single method on the sheet. Although we're passionate proselytizers of arc quenching, which sits at the top of the pyramid, so to speak, in terms of arc flash mitigation effectiveness, we regularly implement zone selective interlocking and differential reeling and other methods in this chart. It is our opinion that the only method in this chart that we do not actively support, and in fact will only implement upon written customer requests, are maintenance switches. And it's not the purpose of this presentation to talk about maintenance switches, but I will tell you that the reason we don't support it is we believe that protective device coordination exists in the National Electric Code for a reason, and overriding protective device coordination when you need it most, which is during maintenance, and it is during energized maintenance for testing, troubleshooting, or calibration, that it is most likely that a fault or arc flash event will occur. Overriding protective device coordination at that point in time is not a good idea. Furthermore, we've seen maintenance switches sometimes left and permanently on positions overriding coordination. For anyone who is interested in a maintenance switch, we would strongly suggest you consider zone selective interlocking instead. But again, for anyone who wants a copy of the arc flash mitigation toolbox, this is your engineering toolbox for all arc flash mitigation methods I'll be discussing today. So in terms of quantifying arc flash risk, the IEEE standard is the recognized mathematical model for quantifying arc flash incident energy, and NFPA 70E is the standard for quantifying risk in terms of personal safety. This again is, in terms of NFPA 70E and personal safety, is not the focus, the primary focus of today's presentation. And because outside of UL type testing, there is no IEEE or NFPA standard we're aware of for quantifying damage to critical equipment assets. I don't know that one will ever be developed because there's so many different types of assets and variables that would be associated with such a standard. But we decided to tackle that challenging topic, and that's the purpose of today's presentation and why we're so excited to present to you today. Because based on previous test data that we've conducted at KEMA with both 480 volt and 15 kV switchgear, we modeled arc flash incident energy at a 6-inch working distance for low voltage assets. So this, by 6 inches, that's not personnel working distance, that's damage within the low voltage asset itself, inside the equipment, inside the switchgear, inside the motor control center, inside the drive cabinet. So that's 1/3 the normal IEEE 1584 working distance. And we also modeled for medium voltage assets at 12-inch working distances. And we based our evaluation on the amount of damage various incident energy levels cause based on a review of previous arc flash incidents. So we modeled 3 different types of arc flash protective relays in our study: Arcteq, Schweitzer, and Multilin. We also ran models with Tech 4's Arcteq arc quencher system. And so you'll see a little bit of the arc quencher system here, but again, this is not an arc quencher presentation. If you're unfamiliar with what an arc quencher is, I would encourage you to contact your L3 sales rep. They have archived arc quencher presentations that you can watch. The overcurrent protection models that we ran for the presentation today include 2 different types of vacuum circuit breakers. The modern, I'll call them fast, 3-cycle, 50 millisecond vacuum breakers, okay, and the latest arc flash vacuum breaker, which has a 12 millisecond clearing time, so which is 4 times faster than the next quickest vacuum breaker on the market. And I should note, before we would go into this, that these are best case models because the majority of vacuum breakers in the installed base in the United States are not 3-cycle breakers. They're 5-cycle breakers. So they rather than opening in 50 milliseconds, they open in more than 80 milliseconds. So, we try to, in the information we're conveying today, we're trying to convey conservative models and reliable data. And we're just very excited to show you what we found. This is a sample or an example of damage in an arc flash incident that was calculated to be 7.8 calories per centimeter squared at the IEEE 1584 working distance. And this equipment was field repairable, but it was extensive field repair. It required approximately 7 days of downtime. And the reason I'm showing you this is I'm trying to give you some comparative equipment damage models. In this case, this is the equipment. Oops, sorry, went too bad. This is the equipment prior to the arc flash event, which is was much higher, 31.7 calories per centimeter squared. And this is the equipment afterwards. So this equipment, once it got above 30 calories per centimeter squared, this equipment was catastrophically destroyed. Right? And once we got to a very high arc flash incident energy level, this is a 48 calorie per centimeter squared at a 36-inch working distance environment. I don't know why that's environment. Both the equipment and the surrounding electrical room and facility were destroyed in a catastrophic fire. You may have seen this video before in our arc quenching presentation, but the switchboard on the left has an arc quencher installed. This was a Square D UL 891 480 volt low voltage switchboard. The test was conducted at 65,000 kiloamperes. And this switchboard on the right is the identical Square D switchboard, has a tripping or clearing time of 50 milliseconds. I'm going to start the video now and look carefully at the left video, if you would, please. At the 4 millisecond mark, you see a brief flash. And at the 50 millisecond mark, interruption with normal overcurrent protection devices. And I want to be clear again, both of these switchboards pass UL type testing. The only requirement to pass UL type testing is to clear the fault and to maintain enclosure integrity. And everything inside that switchboard can be damaged. Okay, the enclosure can deform. The enclosure can, as you can see here, vent hot gas and plasma out of vents and seams. But the enclosure may not rupture. It may not explode. No panel, whether bolted or hinged, may break open. If it broke open, it would have to be returned to the manufacturer for redesign. It would fail UL type testing. But the switchboard on the left was able to be returned to service with the arc quencher in approximately 20 minutes of maintenance, whereas the switchboard on the right was catastrophically destroyed in default event. So this shows a picture of the switchboard on the left, and you can see, okay, that at 0.42 calories per centimeter squared, okay, there was virtually no damage. So I want you to think about that compared to the previous pictures I showed you. So the first picture showed you moderate damage to the equipment. It can be repaired, but approximately 7 days of downtime were involved. The next two pictures I showed you were catastrophic. One was catastrophic damage to the equipment. The highest one was catastrophic damage to the equipment and the surrounding facility. And then now this picture showing a 4 millisecond clearing time. You can see on the bottom right-hand picture some scoring on the bus. But this amount of arc flash incident energy is not that was present here, 0.42 calories per centimeter squared. not sufficient to cause any permanent damage. Approximately 20 minutes of maintenance for cleaning, testing, and return to service. When we talk about total arc clearing time, the clearing time is made up of multiple elements. The first element, and I'm going to model this for you in a animation coming up, is the fault recognition time, the amount of time it takes to recognize the fault. And in the case of an arc flash relay, it's looking for two things. One, it's looking for a high amount of light, generally more than 50,000 lux of light. And if at that same time, the arc flash relay sees a rapid changing current with respect to time, it determines that an arc flash event is in process. So that now we go to B. The relay there's a latency time for the relay to respond to that fault recognition and assert and to close a trip contact and trip a breaker or assert an arc quencher or both. Okay? So the clearing time is either made up is you have to add these together, the fault recognition time plus the relay processing time plus the circuit breaker opening time or the arc quencher closing time. So and as we'll see, circuit breakers by their very nature compared to either the relay or the arc quencher are slow devices. Because of the mechanical nature of the overcurrent protective device. So this is a animated model of what I just described in terms of total clearing time. And we can see here we have our arc quencher device on the secondary. This is a secondary main configuration. Tripping with the trip circuit is to the primary side of the circuit breaker. And I'm going to start the animation right now. And at a quarter millisecond, we have acquisition of an arc flash event in zone 2. And you can see the circuit breaker, which is still closed at this point in zone 2, okay, is feeding that fault as well as the main breaker feeding that fault. The light sensors are picking up that are detecting, okay, more than 50,000 lux of light, which is not difficult since approximately 1 to 2 million lux of light is being generated. Okay. At the 2 millisecond mark, the relay asserts. So it has seen now more than 50,000 lux of light. And if you look at the current transformer as well, and it doesn't even wait for the peak of the sine wave. It sees di dt, a rapid changing current with respect to time. At the same time, it sees the light. Okay, I'll run this again. Two millisecond assertion time, and now the relay asserts. And at the 4 millisecond mark, the arc quencher is closed and the arc flash is extinguished. So this would, in this particular case with an arc quencher system, okay, we can see that the arc quencher cleared the fault. We only opened the last breaker, right? We only opened the last breaker, and now we have to clear the source of the fault. The arc quencher and the main can now be reset. When we look at arc flash relays, the protection methodology for arc flash relays, really the philosophy here is about no intentional delays. We have arc ignition, a trip contact closed, and then either a breaker is going to open or an arc quencher device is going to close, or both. And so the philosophy of all arc flash relays I'm going to show you today follows this basic methodology of looking for light, looking for a rapid changing current with respect to time, and then very quickly asserting an overcurrent protection device and or an arc quencher. And what we're going to see here is the relay is comparatively fast. And in fact, it doesn't really matter how fast the relay is, because the device that is being asserted in the case of a circuit breaker is being told to open is comparatively very slow. So this is an animation of how a typical arc flash relay system would be configured. And we're going to divide this into 3 different zones. There's zone 1 around the secondary main. Here's zone 2, main bus of the switchgear. And then zone 3, the feeder breakers. I'm going to position an arc flash relay. That's the brains of the system. And I'm showing our own Arcteq system here. This device here is a sensor relay. These sensor relays serve essentially as communication gateways for the sensors to communicate to the arc flash protective relay. We have multiple point light sensors in this case. Our system supports both point light sensors as well as fiber light sensors. But my illustration, the models that I'm giving here today are illustrating the point light sensors. So we're going to install the point light sensors in the equipment. This is what we would do in either new equipment or right at the factory or retrofit application at the field, in the field. We would connect the current transformers to the protective relay. Wire in the light sensors. We can wire directly to the protective relay or to the protective relay gateways you see below. We call those AQ101s. And then we connect our high-speed outputs to the binary inputs. Now we connect our trip signals to the circuit breaker and or the arc quencher on the secondary. The equipment that we modeled that we're going to show you today, we modeled the Arcteq AQ110 PLV. This is the fastest arc flash relay in the world with a 2 millisecond assertion time. We brand label this relay to Eaton. The EAFR, Eaton Arc Flash Relay, is this same exact device. Siemens also uses this device from us. They don't brand label it. They install it just as the Arcteq labeled device in their equipment. We also modeled the SCL751, which has a 5 millisecond assertion time. And we modeled the Multilin 350 6 millisecond assertion time. Just for the brevity of the presentation, because I am time constrained today, since the assertion time of the Multilin is so close to the SCL, it's 1 millisecond slower than the SCL 751. In the data I'm showing you, I don't have separate models set up for the Multilin, but essentially the results were nearly identical since there was only 1 millisecond of difference between the 2 relays. But if you're interested, because we did run those models for the Multilin, if you're interested in the Multilin models, please let me know. This is a picture of the point light sensors I showed you in that animation. The sensor on the left is a light sensor. The sensor on the right is a combination pressure and light sensor from our system. This shows you some of the mounting methodologies as well that we ran for our test. So you can see that the sensors can be directly mounted to a panel. They can be mounted on a bracket. The lower left-hand corner here, this is the nub of the sensor that's in the middle here. So the sensor itself is on the other side of this piece of steel. where we just drill a hole and insert the nub into the compartment that we need to detect the light from. A very common method of installing our particular light sensors. This in the bottom right here, you can see a light sensor pointing up, in this case, towards the bus. So light sensor positioning and installation is both a science, I would say, and an art. We have dedicated resources at Tech4 just for determining light sensor positioning based on our high-powered test lab results. In addition to the arc flash relays, we modeled two different types of circuit breakers. The first type of circuit breaker we modeled are 3-cycle vacuum circuit breakers. And I have pictured here a Schneider Electric Evolus 3-cycle breaker. But this would apply to most breakers on the market today. The ABB AMVAC, the Cutler, the Hammer, the Eaton VCB, they're all 3-cycle. The modern, particularly compact vacuum breakers are mostly 3-cycle or 50 millisecond breakers. And we modeled, in addition to standard 3-cycle breakers, we modeled the Tavrida arc flash circuit breakers. So at 5 and 15 kV, the clearing time, excuse me, of this breaker is only 12 milliseconds. So to be clear, the Tavrida breaker, okay, is 4 times faster in terms of opening time than the next fastest breaker on the market. In addition to which, it has a longer warranty. It has 30,000 operations at full load. So it has many more mechanical and electrical operations than any other medium voltage breaker on the market. And of course, it dramatically reduces system stress, as well as its arc flash mitigation capabilities. And to be clear, when the system is used with the arc quencher, the arc quencher is much faster than this. Excuse me. The arc quencher is much faster than the Tavrida breaker, but even in that case, once the arc quencher closes, the Tavrida breaker dramatically reduces short circuit stress. We have no commercial relationship between L3 and Tech4 and Tavrida. We just like using the breaker because we are passionate proselytizers of arc flash mitigation solutions. We also modeled, of course, our arc flash mitigation system and the various components in that system that you see here. So the current and the light sensors attached to the protective relay, attached to an arc quenching device and a control system that guarantees, in the case of a low voltage system, that the arc flash will be extinguished in less than 4 milliseconds. In the case of a medium voltage system, which is pictured in the lower right hand here, that's a picture of the arc quencher. Medium voltage system it quenches in less than 6 milliseconds. So I'll tell you what we did not model yet were low voltage breakers. But I have a question for the audience. One, to make sure you're paying attention at this point. I haven't put you to sleep. But two, to get you to think. And this is my question for the audience. Ignoring the protective relay latency time, which in this case will have whether we're a low voltage or medium voltage breaker. Ignoring the trip unit or protective relay latency time, approximately, what is the difference in clearing time, meaning opening time, between a 3-cycle medium voltage circuit breaker and shunt tripping a modern low voltage circuit breaker? So we're comparing a medium voltage breaker, 3-cycle opening, and we're going to compare that opening time to shunt tripping, either a molded case or a modern insulated case, a medium voltage circuit breaker. So I'm going to just give a few seconds here for you to chat here and in the chat box, and I'll tell you, the first person to come up with the correct answer, we get a correct answer. Mr. McClellan has generously offered a valuable prize, which I added is much sought after and coveted. So the first response we get that is correct will get a free trip to an indoor gun range, which if you live anywhere in the Southeast is appreciated when it's 100 degrees outside. All right, what do we have here in the chat box? All right. Is the presentation frozen or just on my end? Someone has a frozen presentation, 2 milliseconds. All right, nope. Anyone else? Any other feedback? Anyone else want to take a guess at this? Valuable prize. Mr. McClellan, anyone else in the chat box here trying to answer the question? Oh, we got somebody else coming up, going for the valuable prize. Some say 2 milliseconds, 2 cycles. Sherman, you just won. Okay, the answer that Sherman came up with is no difference. He is correct. Okay, there is no difference. A three cycles, approximately 50 milliseconds. The latency time on a low voltage circuit breaker shunt trip does vary somewhat. That's why I use the word approximately by manufacturer, but it's typically between 50 and 60 milliseconds. For example, a square D power pack breaker is between 50 and 60 milliseconds. The master pack, the largest master pack, can be just slightly slower at times. But by the way, I showed you the Evolus breaker before. The same shunt trip used in a medium voltage Schneider Electric Evolus breaker, the exact same shunt trip mechanism is used in their low voltage breaker, the MX shunt trip. So the clearing time is absolutely, in that case, identical. So Shervin, you're the winner. I hope you like shooting guns with Mr. McClellan. Thank you, by the way. It takes courage to write an answer. So thank you to everyone who participated in that exercise. So now to our exciting test results. And this is the home stretch of our presentation. So we ran a number of different models here. And the first model is with the Arcteq AQ110 PLV relay and a standard 3-cycle medium voltage breaker, which is most medium voltage breakers sold today, modern, compact, quote unquote fast breakers. And in this case, the model showed that the label on the gear at the IEEE 1584 working distance, this is a low voltage switch gear, okay, was 5.48 calories per centimeter squared, had an arc flash hazard boundary a little over 4 feet, classically would have been referred to as PPE category 2, although NFPA 70E no longer allows incident energy in PPE category to be printed on the same label. The key information I want to draw your attention to here is the arc flash incident energy inside the switchgear. So anything at a 6-inch working distance, so 6 inches away, for example, on the bus inside the switchgear, and the incident energy was 27.63 calories per centimeter squared. We categorized this based on the earlier pictures and our testing at KEMA as severe damage to the equipment, which is probably, not certainly, but probably not field repairable. So the arc flash relay, let's be clear here, which is the fastest arc flash relay in the world, the Arcteq relay. Okay. Again, the same relay, brand labeled by Eaton, and we provide to Siemens as well. There is no faster arc flash relay on our home planet. Okay? But when you combine that with the relatively slow 50 millisecond opening time with the breaker, it doesn't matter if the relay opened in microseconds, which it can't. Okay? But even if it could, we would still have an unacceptable amount of arc flash incident energy. And the takeaway from this is doesn't matter how fast the arc flash relay is. The breaker is the slow element, which creates that high arc flash incident energy. We then modeled the same super fast 2 millisecond assertion time Arcteq relay with the Tavrida arc flash mitigation breaker. So this was in a secondary virtual main configuration. So we're modeling on the low voltage side of a transformer, but the Tavrida breaker, the medium voltage breaker, is on the primary side of the transformer. And in this case, you can see the dramatic impact on incident energy that that Tavrida breaker had when combined with the Arcteq relay. The arc flash incident energy reduced to only 1.47 calories. Arc flash hazard boundary less than 2 feet now. We're down to category 1. Inside the equipment, at that 6-inch working distance we modeled, 7.44 calories per centimeter squared. And our categorization of the probable damage is that the damage would be moderate, but it's probably field repairable. That falls into that second category I showed you in the pictures earlier in the presentation. The next model we ran is with the SCL relay and a 3-cycle breaker. So instead of an arc flash relay, we have an SCL 751 relay. Now the SCL relay asserts in 5 milliseconds. So that is 2.5 times slower, quote unquote, than the 2 millisecond Arcteq relay. But you can see it just doesn't make a lot of difference, okay? Which arc flash relay you use when you're combining it with a slow, quote unquote, 3-cycle, 50 millisecond breaker. So our arc flash incident energy compared to the Arcteq relay is a little bit higher, 6 calories per centimeter squared, a little bit less than 5 feet of arc flash hazard boundary. But the arc flash incident energy inside the equipment at that 6-inch working distance, which can damage components inside the equipment, is still severe. So whether you have the Arcteq relay or the SCL relay, the damage is still severe and is probably not field repairable. So again, this is emphasizing that it's not about the relay. It's not about the arc flash relay. It's the slow opening time of the circuit breaker. We then modeled the SCL relay, same SCL 5 millisecond assertion time arc flash relay with the Tavrida arc flash circuit breaker. And now what do we get? Less than 2 calories, 1.79 calories, less than 2 feet arc flash hazard, PPE categories gone down, and there's still damage to the equipment, but this equipment, rather than being catastrophically damaged, okay, is only moderately damaged, and it's most probably field repairable. There could be extensive downtime, but it's most likely field repairable. We then modeled the Arcteq relay with an arc quencher and either a 3-cycle or Tavrida breaker. And it doesn't, with the arc quencher, it didn't matter, okay, whether you have a 3-cycle breaker or a Tavrida in terms of the arc flash incident energy. But the Tavrida breaker, the benefit is it with the arc quencher over the 3-cycle is less system stress due to the short circuit system stress of the event. So the Tavrida still had an advantage in terms of stress on the system, but it had no impact now on arc flash incident energy because the arc quencher in this case is clearing in less than 4 milliseconds. So we can see in this model, the arc flash incident energy 0.42 calories, an arc flash hazard boundary of less than 1 foot. The PPE category, less than 1, what used to be called PPE category 0. The bottom line is no ARC-rated PPE personal protective equipment required. And most importantly here, point of our presentation today, inside the equipment, just a little over 2 calories per centimeter squared. Damage to the equipment is low. Normally cleaning, testing, return to service. So we can see between just the models we've come so far. Standard overcurrent protection, with an arc flash, standard arc flash relay with a standard breaker, severe damage in many cases. If we add in the Tavrida circuit breaker, there's still damage there, but it's probably field repairable. And then with an arc quencher, clean the equipment, test it, return to service. Now we're going to look at a standard overcurrent relay. This is our standard overcurrent relay with a 3-cycle medium voltage breaker, and I gave it the assumption here we're going to be within the instantaneous range. Okay, I understand with the standard overcurrent relay this has to be bottled. Okay, we'll just assume this within the instantaneous range. We calculated 8.64 calories over, it is a low PPE category 3 classically, just a little bit under 6 feet for the arc flash hazard boundary. But let's be clear, if you're using just a standard overcurrent relay and a standard medium voltage breaker, now look inside the equipment. It's more than 40 calories at the 6-inch working distance. So the damage to the equipment is catastrophic. It's damage beyond any practical field repair. And beyond that, there is a likelihood that combustion could take place on adjacent assets. It could set the facility itself on fire as hot gas and plasma is vented out of vents and seams in the equipment. In the Model 5A, we compared, going back to the arc flash relay, now we modeled in medium voltage switchgear with a 3-cycle medium voltage breaker. And we could see the arc flash incident energy, 4.64 calories at now a 36-inch working distance. The flash hazard boundary much larger, over 12 feet, PPE category 2. And when we look inside the equipment, even with the fastest arc flash relay in the world, which is the Arcteq relay, okay, it's 2.5 times faster than the next fastest relay, as far as we know. Okay? Is that the available incident energy inside is still high. It may be possible to field repair, but that would probably require extensive downtime. Now we looked at the Arcteq relay in Model 5B. We combined that fastest relay in the world with the Tavrida medium voltage breaker, again in medium voltage switchgear. And the models we did here were 15 kV class, by the way. Okay? And we can see, again, a dramatic improvement due to the Tavrida breaker. Only a little over 1.25 calories of arc flash incident energy on the label, a little over 3 feet in terms of the boundary, so a dramatic improvement in arc flash incident energy. And when we look inside the equipment, the damage has gone down too. There would be moderate damage, but it's probably field repairable. Okay? There could be extensive downtime, but this is the equipment itself, it can probably be salvaged. Okay? And then, of course, Model 5C, our final model here, shows the Arcteq relay with the arc quencher and either a 3-cycle or Tavrida circuit breaker inside now of medium voltage switchgear. And as expected, arc flash incident energy, of course, with an arc quencher is always guaranteed to be less than 1.2 calories. In this case, it's 0.54 calories. Arc flash hazard boundary is a 1.3 feet. PPE category, again, is 0, no arc rated personal protective equipment required. And inside the gear, at a 6-inch working working distance, 1.56 calories per centimeter squared. The damage to the equipment, again, is low. Normally just cleaning, testing, and return to service. In a subsequent presentation, we may be adding animated models similar to the previous animated model I showed you as well. Make sure I'm not running over time here. No, we're good. This shows, again, from an earlier, I had this in an earlier arc quencher presentation, compares in a ground fault environment from one of our high power test lab tests between an arc quencher and an arc quencher with a circuit breaker and an arc quencher by itself. The red line shows the arc quencher and shows the circuit breaker by itself. The red line is the circuit breaker by itself. The blue line is the arc quencher and the circuit breaker together. And the next model shows a very similar test. This is a 3-phase test. And again, the red line showing a circuit breaker alone versus an arc quencher combined with a circuit breaker. The bottom line is that the amount of system stress associated with any type of arc flash event, even with the arc quencher closing and creating a bolted fault, okay, is much less than with the circuit breaker by itself, because the arcing fault and the slow opening time of a circuit breaker is where high asymmetrical voltages and peak currents tend to occur that create catastrophic damage to the equipment. This from my earlier arc quencher presentation is my favorite medium voltage graph. It shows the red pressure curve here, the breaker opening at the 50 millisecond mark, and you can see the breaker did its job. It did what it was designed to do. It protected the insulation integrity of the conductors. It opened before there was a cable fire, copper fire, or steel fire. It prevented any of that. We could see at the intersection point of the arc energy and the breaker opening at 50 milliseconds that we're right around a little over 10 calories per centimeter squared of arc thermal energy. So this gray energy is the thermal or the burn risk. The red line here is the arc blast, the pressure curve. And we can see that the peak pressure, which can collapse eardrums and lungs, is reached before the breaker opens. So if you're within the arc flash hazard boundary, when that there is still that risk associated, which is why PPE is required, and also why the NFPA 70E will never approve PPE above 40 calories per centimeter squared, because even if we can protect you from the burn, we cannot protect you from the blast, the sudden pressure change that occurs in these catastrophic events. This is a similar model based on a 480 volt modeling comparing conventional overcurrent protection. We could see the dramatic benefit in terms of calories per centimeter squared of zone selective interlocking. And another quantum leap in arc flash mitigation benefit if we added an arc flash protective relay. Okay, and again, we assumed a slow relay in this case, many times slower than our 2 millisecond relay. And then of course the arc quencher all the way in the right has the lowest possible incident energy, always below 1.2. So the 3 practical questions we think you should always ask yourself or any customer you're working with if you're an engineering consultant is, how important is your facility uptime and power system continuity? Because there are choices here, and we would never argue that arc quenchers are for every application. But if you want to have reasonable assurance that both your people will be protected, personal protective, arc-rated personal protective equipment will be eliminated, and most importantly, the asset itself will be protected from catastrophic damage. The arc quencher certainly bears consideration, and the Tavrida fast-acting 12 millisecond opening time circuit breaker can bear consideration with or without an arc quencher. I think it's important to ask how important it is to reduce arc flash hazards. And again, if someone is satisfied with 8 calories per centimeter squared at the working distance, they don't care if the equipment itself is catastrophically damaged. You don't need an arc quencher or a Tavrida breaker to accomplish those goals. Those can easily be accomplished via differential relaying and or zone selective interlocking. I see I have my number sequence wrong here on this slide. And 3 is, does the facility benefit by eliminating arc-rated PPE? Because I'll tell you what, it's not just about lack of comfort. Arc-rated PPE compromises dexterity and it compromises visual acuity, both of which lead to mistakes and drop tools and equipment. And drop tools and equipment is the number 3 cause of arc flash events. So there is a direct safety correlation between dexterity and safety. And that concludes my presentation for today. I am open for questions. We have 4 minutes before the hour. I'll certainly stay after the hour I do want to be respectful of people's time. And again, it was a privilege to present to you today as we examine what happens inside equipment when an arc flash event occurs. Michael, you can help me out by reading some of those comments to me.
Great, Mike. As always, wonderful, wonderful job. Your technical expertise in this field is unmatched.
Yeah.
You're
so kind. I come here to get all those positive words of encouragement that I can't sometimes get at home. So thank you, Michael. I appreciate that.
You're very welcome. There is a good question here. Theoretically, could arc quenchers be used in applications such as solar farm combiner enclosures? These are often opened for maintenance and would then be exposed to sunlight. Is there a way to account for that and still be functional in an arc event?
Right. So the arc flash relay cannot be fooled by sunlight, right? Because again, two process variables must be present at the same time. You must have the more than 50,000 lux. If you open it to sunlight, the light sensor will assert. Sunlight's about 100,000 lux, so that will assert a light sensor. But unless you also at the same time have a rapid change in current with respect to time, the arc flash relay will not assert. And all the arc quencher installations done globally by Arcteq, they've actually never had a nuisance assertion. You would think such a thing would be statistically possible, such in the same way nuisance circuit breaker assertions are possible. But the reality is that the way these systems are designed now, with all the diagnostics that run on them, and the fact you need those two process variables, both current and light, it can absolutely be installed on but we have outdoor installation. First of all, we have installations like this already as a solar farm combiner. Absolutely. In fact, we've got one at Tesla in Arizona in the solar farm. So thank you for the question. Great question.
Mike, would the quencher go on the DC side? Or I guess the question is, could an arc quencher be used with a DC system?
No, we have to, it's an AC quencher, so we quench on the AC side of the inverter. We always quench on the AC side. We have not yet conducted high-powered test lab testing for a DC-rated arc quencher. That's a great question. In the same way, I think as everyone's probably aware, we really don't have an IEEE 1584 equivalent for DC, right? We have we know DC causes arc flash. That's how an arc welder works. But the models we have for DC arc flash are strictly at this point theoretical. And we're just waiting for a enterprising power system engineer and someone with a lot of money to develop an IEEE 1584 for DC. And the same applies to arc quenchers too. So great question, but at this point, the quenching is always done on the alternating current side of the inverter.
Wonderful. Mike, thank you so much again for your time. It's an important topic, and you did a wonderful job of addressing the subject that I think a lot of people are ignoring, which is it's wonderful to have arc flash relays like the SEL 751A and the multi-lin 350 and 850, but it's also important for engineers to realize that you can only do so much to eliminate incident energy with the relay. At some point, if you want to get to category 1 or 0, the breaker opening time has to be considered.
Absolutely, which is why the Tavrida breaker is a reasonable middle solution, whereas it's fast. By the way, I see another question here from William Shiri. It says, for an older facility, would implementation of arc flash relays sensors be cost prohibitive? How much time is needed to install on a typical MCC? Okay, that's a great question, and the answer is arc flash relays. The arc quencher is the more costly system. Again, the average cost of an arc quencher system is $75,000. So for a low voltage system, so they understand those can be that seems expensive until your equipment's catastrophically destroyed, or someone's injured or killed. All of a sudden, that seems very inexpensive. But if we're looking at just arc flash relays alone and sensors, okay, the cost of the relays and the sensors comparatively is fairly small. I mean, an individual point light sensor is less than $200. Okay? But in terms of the time needed to install in an MCC, we've done a lot of this and retrofitted an MCC. So I would tell you this, I'll be very frank here. Motor control centers are the most complex piece of equipment on which we install arc flash sensors. We use a combination of point light sensors and fiber light sensors in the motor control center, and it does involve removing the buckets, because we have to. We typically run the fiber light sensors to the left side of the bucket. And then we have point light sensors guarding the bus, so we're weaving fiber optic cable up and down through the MCC. So I can tell you this: it takes 2 men on a large MCC. Okay, we're talking like a 20-section motor control center. It takes 2 men an entire workday, 8 to 10 hours. To remove all the buckets, disconnect all that, install all the light sensors, and put the buckets back in. So that's best done probably during an annual maintenance outage when you have downtime. The easiest piece of equipment to install in is either a low voltage switch board or metal enclosed switch gear on the medium voltage end. Those are simple. A little bit more complex when you get to low voltage route switch gear or metal clad gear. That's kind of in the middle. And boy, motor control centers are the most time consuming asset on which to install arc flash sensors. Most of it, by the way, most variable frequency drives are easy in comparison, depending on the drive configuration. But MCCs are, from a labor point of view, definitely the most time consuming. Great question. Thank you for that. The next question is, can you retrofit the Tavrida breaker into Schneider switchgear? And the answer to that is, I can't, but Michael McClellan works for people who can. Okay, so we don't do that ourselves at Tech4. My answer to that is, please contact your local L3 sales engineer for a solution. Any other questions? Michael, are you still there?
Yes, I am. Thanks,
okay.
Mike. Great job.
Okay. Thank you. Again, we've run way over now time, so in our Q&A, and but you've given me so much credit, Mr. McClellan. I do want to thank Michael here. Although we were on the execution phase here, this whole webinar was his idea, and he's driven a lot of these ideas. So thank you so much, Michael. It's people like you that motivate us to travel into uncharted territory. I want to thank you for that. You have a great afternoon. Everyone be safe. And if you have any questions, we'll be in touch. Thank you. Bye-bye.